Hello, I'm Omar and I'll be talking about the Deep Learning on Trajectory Images fourth year project along with my partner Santosh. Our project aims to classify unmanned aircraft as either fixed or rotary wing drones or as birds using their simulated trajectories. To increase public safety, there is an urgent need to track and identify unmanned aircrafts. There have been instances in the US, the UK, and Canada where drones have collided with planes. This demo will first go over how the radar simulations were produced using the StoneSoup open source framework. Then we will discuss how to use machine learning and deep learning techniques to make an accurate classification on the aircraft.
In the real world, it is hard to track a drone perfectly. Two main reasons for this is because there are external factors as well as missed detections. External factors can include an error with the tracker that leads to tracker creating random inaccurate detection. The tracker will think it is tracking a drone when in reality it is not tracking anything. To mimic noise, we use StoneSoup to add clutter. As shown in the image, the green dots spread across the image is the clutter. The blue dots are the measurements, which are the detection.
From the previous simulation, we have a bunch of detections and clutter that are generated near the ground truth. It is now time to create the track. First, the initiator will determine where the track starts. Then a hypothesizer will determine where the next point is given the detections. So far, we have shown all our simulations as 2D figures, but in reality, a drone or a bird actually has an associated altitude component. The following simulation shows the same rotary wing flight path, but incorporating the altitude feature. We can see that in the second loop, the rotary wing drone increases its altitude, and at the end, it comes back to the altitude it started at.
These 3D simulated graphs, compiled using StoneSoup, can be broken down into 6 features. These features are the estimated latitude, longitude, and altitude, as well as the estimated velocity for each of these 3 directions. Unfortunately, in the real world, a tracker cannot track a drone indefinitely. It can realistically only track a drone for a couple of seconds. Since our graph spans over a couple of minutes, in order to make it more realistic, we broke the graph down into 40-second segments. These sub-trajectories were used to create, train, and test our machine learning model.
On the screen right now are the images of the rotary wing subtrajectories. As you can see, they're smaller and they include images where the drone is hovering, like this image right here. Next, we can see the images of the fixed wing class subtrajectories. Clearly, we can see from these images that the subtrajectories are longer since they cover more distance. The difference between the two images will be key to training our deep neural networks.